Good morning, class. Today we will take up Chapter 4, General Motion of Rigid Body. Instantaneous Center of Zero Velocity. In the last class, we mentioned if the base point is of zero velocity, the problem of finding velocity will become very easy. Does such zero velocity point exist in rigid body in general planar motion? The answer is positive. For example, this is a wheel rolling without slipping on a plane. When a wheel rolls without slipping, point A is the point of contact with the ground. Since there is no slipping, the point A will have the same velocity as the ground. So the velocity of contact point A is zero because ground is at rest. Point A is called instantaneous center of zero velocity. If a point with no velocity, this point can be called instantaneous center of zero velocity. Now, 16.6. Instantaneous center of zero velocity. After this class, the students will be able to A. Locate the instantaneous center IC of zero velocity. B. Use the IC to determine the velocity of any point on a rigid body in general planar motion. This is the objectives of this lecture. First, let's discuss how to locate a IC. To locate IC, we can use the fact that the body rotates about IC at the instant. So compare with the rotation about a fixed axis. Let's review of the velocity distribution along a radius of a disk in rotation about a fixed axis. In this diagram, we can see along a diameter AB, all the points have different velocity, but there is very clear relation. They are proportional. They are proportional to each other. That means as the radius increases, the velocity increases proportionally. And the direction, those directions are all perpendicular to the diameter. So this is what we have learned in the rotation of a body about an axis. Today we will use these conclusions to locate the IC of a body in general motion. So then the velocity of any point on a body is always perpendicular to the relevant radius, i.e., the relative position vector from the IC to the point. So this is the conclusion from a distribution law of an object rotation about an axis. Now let's come to the first case. In this diagram, we can see the object, rigid body, moving in a planar motion. That means it both translate and rotate. So if the velocity VA of a point A on the body and the angular velocity omega of the body are known, so we have known the two quantity. One is the velocity, the other is omega. Now, how can we determine the IC based on these two known quantity? In this case, IC is located along the line drawn perpendicular to VA at A, a distance from A. Our A relative to IC equals to VA divided by omega. That is, the IC lies at upper right of A, since VA must cause a clockwise angular velocity omega about the IC. So compare this diagram with the diagram in the last slides. IC is just like the axis, fixed axis at that diagram. And RA relative to IC is a radius, because we first know the VA. So radius at A should be perpendicular to VA. So we draw A to IC perpendicular to the VA. So we get this line segment AIC. Then why the IC located at the upper right side of the A? Because we should make the omega and the VA consistent. So only when IC located in this side, then the object rotates about IC clockwise and consistent with VA. So this is why we get this IC, locate this IC this way. Okay? So this is the first case. I just mention it as the definition method. Use the definition of the IC. We can finally figure out the location of IC. Now, second case. In this diagram, we can see there are two velocity, VA and VB. We have already known their directions. Only directions are known. And these two velocities are not parallel. So here I call the directions of two non-parallel velocity. So they are not parallel. We know the two directions of the velocity. In this case, in this condition, how can we determine the IC? To answer this question, we should also make comparison of this diagram between the diagram we have already discussed in rotation about an axis, about an fixed axis. So now we already know two velocity at A and at B. Then according to the result that the velocity should be perpendicular to the radius at each point. So we can draw the line AIC and the BIC perpendicularly. So when these two imaginary radius coincident at IC, so this IC is the axis, and we can make these two velocity consistent when the body rotate about IC instantly. Okay, so this is a drawing method. That is, first construct straight lines respectively from A and B perpendicular to VA and VB. The point of intersection of the two lines locates the IC of the body. So this is the method, second method. The third case is when the magnitude and direction of two parallel velocities at A and B are known. So the conditions are different. Here, the two velocities, both magnitude and direction, are known at A and B. But the two velocities are parallel. So in this case, we compare this diagram with the velocity distribution. That's the right diagram. Okay. So from the right diagram, we can see if two velocities are parallel, they should belong to the same diameter, right? And at the right diagram for the left case, the velocities A and B are opposite direction, with opposite direction. So we can judge from the rotation about an axis, from the distribution, we can judge A and B should be on same diameter, but at the two sides of IC, right? And the velocity at VA and at VB is proportional to the radius. So based on this law, we just make the connection lines from the head of the two velocity vectors. That is, from VA, the head, to the VB head, we draw these connection lines. And this line will have an intersection with the diameter AB. So in the left case, the IC is use this method to finally locate. And at the right case, VA and VB parallel and with the same direction. So compare this case to the distribution, velocity distribution of an object rotate about an axis, about an fixed axis. We can judge the AB is at the same side of IC. that means A, B are on the same radius. And also use the distribution law, the velocity is proportional to the radius. So we also use drawing a connection lines from the head of VA to the head of VB and extends this line all the way down, all the way up until across with the diameter or with the radius, right? So this intersection is the IC. So in the left case and the right case, both are using the method of drawing connection lines of the head of two velocities and finally get the intersections for the two cases. The intersections are instantaneous center of zero velocity for this third case. So this is a conclusion. The location of the IC is determined by referring the velocity distribution on a radius of a body rotating about a fixed axis and using the method of drawing connection of the two heads of velocities, then we finally can locate the intersection. That is the IC. Okay, this is the method to locate intersections for the third case. In third case, there is a special case, further special. In this case, A. In third case, if VA is equal to VB, so when use the method of drawing connection lines, drawing the head of VA and VB, then you will get an intersection at infinity and a very distant point at infinity. So the IC is located at infinity. B. Another case is that in the second case, if directions of velocities of 2 points A and B are the same in the case 2, originally case 2 with the velocities with different directions, but now if the two velocities are parallel, and the connection of A and B are not perpendicular to the velocity. Now this is the case B. In this case, we use the method in second case. We draw perpendicular lines of both velocities, and also they will intersect at infinity. So in case B, also we get IC in infinity. So these A, B, both cases is a very special case. What is the meaning of a IC located at infinity? Just think. The IC is also located at infinity. Now this is the meaning called instantaneous translation. When the IC is located at infinity, omega will be equal to 0. And the body is translating at the instant. So we call this state instantaneous translation. Instantaneous translation. Here is an example. This is a crank and a linkage mechanism. Crank linkage mechanism. When the crank rotates to a vertical position, so the VB is horizontal, and the piston C is always horizontal. Velocity is always horizontal. So at this position, when you use, this case is just the case B, is like case B. So when you use join connections, join the both perpendicular lines to the velocities, they will have intersection at infinity. So we can say at this time, at this instant, linkage BC is moving instantaneous translation. It's doing an instantaneous translation. Okay? So this is a very good example. This is a commonly, we all often see this case. So at this instant, omega equals to 0. That means at this instant, all points on the linkage are of the same velocity. So this case is called instantaneous translation. But to remember, it is different from translation of a rigid body, because acceleration of each point for this linkage is generally not equal. The velocities at each point of this linkage is equal, but acceleration of each point in linkage is not equal. Therefore, instantaneous translation and the translation are totally different. So don't make confusion with these two motions. Okay? Now the final case here is fourth case, have already been shown. When a rigid body is rolling without slipping, the contact point between the body and the track is instantaneous center of zero velocity. This is actually true. This is true because just now we have already analyzed. The ground is at rest. The contact point A in the wheel will have no slip. That means the velocity of A should be 0. So according to the definition, the point A is at the window and at the wheel is IC, is the instantaneous center of zero velocity. But you should know that the instantaneous center is just has the instantaneous meaning. That means only at this instant, this contact point A is instantaneous velocity. But after a time interval, originally contacted point will leave the ground, become moving. So at another instant, maybe another point play the role of zero velocity point. So you should be very clear about this meaning. Zero velocity point only has the instantaneous meaning, not forever, not always. Okay? For the other case, for example, a disk roll without slipping on a surface, or for a we call the planetary gears system, the two gears, the planetary gear were rolling without slipping on the fixed gear. The contact point at this instant is C. So at this instant, C is zero velocity point. Okay? Now, velocity analysis. After we get the location of instantaneous center of zero velocity, we can make very clear analysis about the whole body, every point, any point on the body. We can analyze its velocity. The motion of any point at the rigid body undergoing general plane motion can be determined easily once the instantaneous center of zero velocity of the body is located. For example, here, if the IC is the instantaneous center of zero velocity, then we can use the concept at this instant. All the point is rotate about the instantaneous center. But also you can begin with the method of base point discussed in the last class. By using the base point method, take IC as base point. Then the method will give the result VA equals to 0 plus omega cross RA IC. VB equals to 0 plus omega cross RB relative to IC, etc. The body rotates about the IC at a given instant, as shown in this kinetic diagram. Okay, since you have already know the nature property of this motion, later on, in method of IC, the magnitude of velocity of any arbitrary point can be directly calculated by this formula. V equals to omega R. Only solve for magnitude of the V. So this is a scalar formula, where R is the radial distance from the IC to the point. The direction of velocity is perpendicular to a corresponding radius. So you just substitute the R with the radius of each point, A, B, and C, relevant radius, substitute them into this scalar formula. Then you can get the V at each point. Omega is the global quantity. Only one omega, right? And consistent with the angular rotation direction. Now, let's come to see an example. Example 16.6. This is also a mechanism called crank and linkage mechanism. At this instant, we have already know the velocity of the piston. Here is a block D. Vd is equal to 3 meters per second. This is what we have already known. Other dimensions have been shown in the diagram. Now find the angular velocity of links AB and BD. There are two unknowns should be solved. The angular velocity of AB and the angular velocity of BD. First, we can make a brief analysis about the total mechanism. And in this mechanism, we often analyze. Crank AB is doing rotation about the fixed axis A. And BD, which is in planar motion, general planar motion. So, since we have already know the velocity of VD, then we can take BD as the object of study first. So we take BD as our object of study, then analyze the IC, that is the instantaneous center of velocity, of zero velocity. Then we can get the relation between omega BD to the VD, right? So in this way we can solve for omega BD. Then for crank AB, if we know the velocity of B, then we can also use the formula solve for a rotation about a fixed axis. We can solve for the omega of AB rotate about axis A, right? Okay, now let's do in detail plan. First, locate the instantaneous center of zero velocity of link BD. Because this belong to the second case. This example belongs to the second case. That is, we know the velocity of 2 points. One is point D, whose velocity is horizontal, and the other point here must be B, point B. The velocity, direction of velocity is perpendicular to AB, So it's just in this special instant, because the angle is 90 degrees, so the velocity VB is along BD in this instant. So we draw the two perpendicular lines of the two velocity vectors. And then finally, we can get an intersection, IC, here, intersection IC. The instant solution, the instantaneous center of velocity for BD is located at the intersection of the line segment drawn perpendicular to VB and VD. Now that VB is perpendicular to linkage AB, therefore we can see that the IC is located along the extension of linkage AB. Right? We have done the IC. So then we can analyze the AB. AB do the rotation clockwise about fixed x A. Right? Using these facts, geometrically we can determine the position. Use this radius RB relative to IC is equal to 0.4 tangent 59 degree, and finally which is 0.4 meter. And likewise we can determine the position vector RD relative to IC, which is equal to 0.466 meter. Since the magnitude of VD is known, the angular velocity of link BD can be found from this relation. VD equals to omega BD times RD relative to IC. Omega BD then can be found by VD divided by RDIC. Substitute the real data, real value into this formula, then we finally get omega BD is equal to 5.3 radians per second. Okay, this is the first solution, the omega of BD. Then this is positive, that means the assumption of rotation sense is correct, so which is counterclockwise. Okay, then for crank AB, linkage AB rotates about A. So omega AB is equal to VB divided by RB to A. Then use the method of instantaneous center. Then we can determine VB by RB to IC times omega BD, and then divided by RB to A. So finally, the omega AB is equal to 5.3 radian per second. And with the sense clockwise, the second omega is clockwise. Okay, these are two solutions we have already attained. Okay, this is the example. That's all for this class. Now is the homework. Thank you.